Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems, and we will continue with our discussions on this Routh-Hurwitz criteria that we started off about 2 lectures back. So towards the end of the last lecture I tried to put in a number of facts together to give you a complete picture. So let me quickly summarize those facts, some of them which we have already spent a considerable amount of time in sort of establishing, I would not say proving, because we did not go about it in the rigorous fashion that would stand the test of a mathematician's scrutiny, but nonetheless for the purpose of this course and for maybe an undergraduate curriculum, I suppose you would agree that we have presented convincing arguments to establish that the conclusions or the deductions or inferences we draw from this Routh tabulation are indeed correct. So let me summarize some of the pivots or the pillars on which our observations stand. The first, and probably the one that I have least referred to, probably I just referred to it just once in the last lecture, but you see there is this thing about all coefficients of a polynomial have same sign. So this is actually a necessary condition for the polynomial to have roots, or rather all roots, in the open left half plane, in the sense that if this condition is violated, then you know for sure that such a polynomial cannot have all its roots on the open left half plane. On the other hand, just because a polynomial satisfies this criteria, you cannot immediately deduce that this polynomial will have all its roots on the open left half plane, and indeed we saw such a counter example, right. We saw this counter example in the previous class, for which we actually showed you the step, the algorithmic step, and then we showed you the shortcut by means of this Routh tabulation. Okay. So at least this first fact, this observation is well and truly made. What about the second point? The second point, of course, this is something which we have dwelt on for considerable amount of time, and we will not belabor the point too much. We have seen this, so I am not going to explain what that interlacing is. By now you already know. In case you want to revisit it, please do visit the last 2 lectures to understand what this interlacing is. Hereafter I will just refer to it as the interlacing property. So this interlacing property, okay, if a polynomial satisfies this interlacing property, it is a necessary and sufficient condition. Okay. So it is a necessary and sufficient condition that the polynomial has all its roots in open left half plane. Okay, that is a second observation of some that we are going to make. Okay, a few observations that we are going to make. That is the second of those observations. The third observation is, now just to refresh your memory, once we figured that this property, this interlacing property, is the same as having all the roots of the polynomial in the open left half plane, we have reckoned, okay, maybe we have a tool. But then we figured that, well, in order to check for this interlacing property, eventually you again end up solving for roots of polynomials. Which polynomials? Precisely the even and the odd parts of the polynomial, or rather the real and the imaginary parts of a polynomial, right. When you when you substitute S is equal to j omega, where omega can range from 0 to infinity, right? It is precisely that polynomial whose roots we are looking to evaluate. But then again, we started with the problem of determining whether the roots of a polynomial are in the open left half plane, and then this is like a circular logic. We end up at a situation where this interlacing property dictates we find the roots of two more polynomials, albeit of a lesser degree, yeah, but that still doesn't remedy the situation, because as I said, beyond 4th degree polynomial you don't have closed form expressions for the roots of a polynomial. So if you start with a 20th degree polynomial and I give you two polynomials of 10th degree each, yeah, for all practical purposes, I mean when you're computing on a computer you'll say, yeah, it's easier to evaluate the roots of a 10th degree polynomial than a 20th degree, right, less computational load on the system. But if you're looking for closed form expressions, then the 10th degree is as bad as the 20th degree, right. So we don't want to be in a situation where we have to in fact again evaluate the roots of some polynomial, because that's what we are trying to bypass after all. So that called for this search for an algorithm that will allow us to have a polynomial and then reduce its degree subsequently, and to infer the something about the location of the roots, whether they are in the open left half plane or not. In other words, what we then tried to do was cook up a degree reducing algorithm, okay, such that if the original, which is the higher degree polynomial, satisfied the interlacing property, then so would the reduced degree polynomial. Notice we are not talking about the locations of the roots of the original polynomial or the reduced degree polynomial. We are just saying that if the original polynomial satisfies the interlacing property, which means that the original polynomial has all its n roots, n is the degree of the polynomial, so n roots on the open left half plane, then so would this reduced degree polynomial potentially of a degree n minus 1 also meet this interlacing property and therefore have all its n minus 1 roots in the open left half plane. We are not trying to map a relation between the original n roots of the n degree polynomial, the higher degree polynomial, and the n minus 1 degree polynomial that we have now obtained by this algorithm. No, we are not interested in that. So long as they have all of their roots in the left half plane, we are happy. Why? Because then we can keep successively reducing the degree and checking, and of course the important thing is and vice versa, which is to say that if the original has all its poles, all its roots on the left half plane, so does the reduced degree. If the reduced has all its roots on the left half plane, so does the original. And you can see again, let me sort of at the cost of again boring you maybe, let's revisit this. Yeah, this is how we argued. So listen, we went from the original P to the reduced degree Q, and we saw that Q retained the odd part, yeah, where the original polynomial was even, and the even part got reduced like this. And we then saw that if the original polynomials P odd and P even, if their roots interlaced, then so would the roots of Q odd and Q even. Now if you go about it in the opposite fashion and you write down this P even in terms of Q even and Q odd, yeah, you have two equations. Look, you have equation number 1, you have equation number 2. So here we are interested in writing Q odd and Q even in terms of P odd and P even. Now of course by an inverse relationship, if someone asked us to write down the P even and P odd in terms of Q even and Q odd, that also we can do. Of course the first expression would be the same, we will just make P odd the subject of the formula and write P odd is equal to Q odd. In the second expression we would just write P even is equal to Q even plus S into an by an minus 1 times p odd and then substitute p odd by q odd. So basically that would tell us that p even is equal to q even plus s an upon an minus 1 into q odd, okay. So that is the inverse map in some sense, no, right. So basically what we are saying is, of course, if interlacing of P implies the interlacing of Q by the same argument as we presented here, I am not going to revisit that argument, we showed you that the sign changes between any two successive roots of the even part, the sign of the odd part, yeah, undergoes a switching, okay. So you check the sign of the even part at the two roots of the odd part, or you check the sign of the odd part at the two roots of the even part, and you will see that the signs are opposite, alright. So because of this opposite signs, we have deduced that if the original polynomial has interlacing, the reduced has interlacing, and now because I have given you this inverse map, you can try it as an exercise actually. So try it as an exercise and check that if you take now that the reduced degree polynomial, this Q polynomial satisfies the interlacing property, so would the original polynomial P. So we can go back and forth up this ladder, okay, from lower degree to higher degree, from higher degree to lower degree. So that is a very key and important observation that we make in this point, okay, at this point, okay. So and it is very crucial that this vice versa part, one really cannot overemphasize the importance of this, okay, because this then tells us that if we can somehow check for the interlacing of a reduced degree polynomial, once we have cooked up an algorithm, suppose we have this algorithm, then if we can say something about the interlacing, if we can see that the lower degree polynomial obtained by employing such an algorithm which retains the interlacing property, yeah, then if that satisfies the interlacing, then the original polynomial will also satisfy interlacing, okay. Now the point is, we do not actually want to check for interlacing, because we have already seen that the other necessary condition at least for interlacing to be true is that all the coefficients of the polynomial must have the same sign. Now if we reduce this degree of this polynomial sufficiently, you see, for a quadratic polynomial at least we know, yeah, that all coefficients have same sign is the same as, it goes both ways, all roots of polynomial are in open left half plane, okay. So the strategy is, we do not want to actually check for interlacing, because again remember at any stage you want to check for interlacing, you have to evaluate roots, which we want to avoid at all costs. So now that we have this degree reducing algorithm that we have shown you, what we will do is, we will reduce it until we reach this quadratic stage, yeah, and then at this quadratic stage we check. Now we do not have to check for this this interlacing property. So at this quadratic stage we check if all the signs of the coefficients are the same, yeah. If they are the same and there has not been any sign change in any earlier stage, because remember at any earlier stage, maybe at the cubic stage, at the 5th degree stage, at the 12th degree stage of reduction, if there ever was a sign change, you can forget about all the poles being, all the roots being on the left half plane, because it is a necessary condition, okay. So just because up until that point in time all the coefficients have had only positive values, does not tell you that the roots of the polynomial will be on the open left half plane until you reach the quadratic stage. But if at least at any stage you violate that condition, then you are sure that you are violating the sign condition and therefore the interlacing property, and therefore this gives us a test. So then we showed you through an example such as this that indeed you can carry on this degree reduction like this, but of course for bigger or higher degree polynomials this becomes a lot of steps and a lot of calculations and bookkeeping to be accounted for. So therefore we went for this kind of a shortcut, a tabulation, where we split up into the odd and the even part. The first two rows are very straightforward to write, and thereafter we remember this shape, yeah. There is a minus sign here and there is a multiplication here and a multiplication here. So, this shape. So, just going along that direction, we will probably take another example and show you how this works. We will show it in both ways. We will first take it in this fashion like we did here, this algorithmic step, and then we will show the corresponding Routh array. So, that just to illustrate, it will be another illustration of the same fact. But before that, I want to draw your attention to another interesting point. I told you that while we set about to determine if all the roots or all the roots of the polynomial are in the left half plane, open left half plane, this Routh array ends up giving us more information. Suppose all the roots are not on the left half plane, okay. Then Routh array does not just stop at telling you that, well, forget about this polynomial, it does not have all its roots on the left half plane. Routh array in addition to that also tells you how many are on the left half plane and how many are on the right half plane. So, as a bonus, as if Routh array also gives us the distribution of the roots in the OLHP and ORHP with a bit of modification, even distribution on the imaginary axis. We will see that in a while. That's actually more interesting because it's a singular case. Okay, we'll see that shortly. But for now, you can think of it like, not only does the Routh array tell you if all your roots are on the left half plane, if they are not, then it will also tell you how many are on the left half plane and how many are on the right half plane. This is a fact that does not readily follow from the analysis or kind of the sketch we have given so far about this algorithm, but we will visit that shortly. For now, let me take another example to convince you and also to illustrate how to go about this Routh array. So, let me take another example, this time a 4th degree polynomial. So, suppose PS is s to the power 4 plus 9s cubed plus 35s squared plus 50s plus 24. Okay. So, first thing first, I am going to split it up into even and odd. So, PS is equal to P even s plus P odd s. So, this is an even degree polynomial. So, the even one will be the highest, will contain the highest degree term. And of course, when the coefficient of the highest degree is 1, we call it a monic polynomial. Okay, monic polynomial. So, that just means coefficient of highest degree is 1, unity. So, even if it is not a monic polynomial, ultimately if you want to study the root, just pull out the an term, yeah. Even if it is not monic, ultimately you can reduce it to a problem of studying the monic polynomial only, right. All that you need to do is pull out the an, yeah, and divide every other coefficient by an, right. And because it is a highest degree term, so an is not equal to 0, so you can always divide, because if an is equal to 0, then it does not remain a 4th degree polynomial anyway, right. So, eventually this problem can always be reduced to one of studying a monic polynomial. So, what is this even part? S to the power 4 plus 35s squared plus 24. And what about this odd part? It is 9s cubed plus 50s. Okay. So, now if we go about it, we will retain the odd part. So, now let us pass this through the algorithm. So, at the first step of reduction, degree reduction, we retain the odd part because the odd part does not contain the highest degree term, but we reduce the even part. How do we do that? We take s to the power 4 plus 35s squared plus 24 minus, so we have s by 9 is what we have to adjust with, no, because now we have 9s cubed plus 50s, okay. So, you see, if you adjust by s by 9, then you can manage to cancel this s to the power 4. Yeah, so then you have this 9s cubed plus 50s plus s to the power 4 goes off, you are just left with 35s squared minus 50 by 9s squared. So, I wonder what the value is, 9 5s are 45, 9 3s are 27, so that is 315 probably, yeah. So, it is 315 minus 50, that should be 265 I believe. So, it is 265 by 9, 265 by 9 s squared, unless I am much mistaken, I hope I am not, I don't want to mess up this calculation, plus 24, right. So, now you see I am going to go to the next stage. At the next stage, my goal is to reduce this fellow. So I retain 265 by 9 s squared plus 24 as it is, and then plus 9s cubed plus 50s minus, what do I need to multiply this by? I need to multiply this by 9 times 265, sorry, so 9 times 9 over 265, yeah. So this 9 over 265 will cancel out this 265 by 9. So it will be a nasty calculation, as I can see already, yeah. Right. So now if I want to write this down, let me recall that, let me repeat that step. So it's 265 by 9 s squared plus 24 as it is, and then plus, of course, this s cubed goes. So I am only left with this s, thankfully just one nasty calculation, but this, sorry, I missed this s, no, yeah, of course it has to be multiplied by s in order to cancel out, take down this s cubed. So this 9s cubed goes automatically, that is the way I have designed it after all, so it has to go, no, 9 cancel, 265 cancel, this 9 remains outside, so it is basically 81s by 265. But the nasty calculation would be, and now I have to do this, 50 minus, and look at this nasty bit, it's, what is it? It's 81 by 265 into 24, right? It's very bad, 81 by 265 into 24, but I shouldn't complain, things could have been much worse after all, okay. And then if I go to the next step, of course I will leave it to you to complete this. Now my goal is to get rid of this fellow. So what I am now going to do is, I wonder what this fellow's value is, 50 minus 81 by 265 into 24. What you can clearly see is that this is a positive quantity, right? I mean, you can keep reducing this, yeah, you can keep reducing this to P1s, but at this point only I make the claim that you can already see it's a quadratic polynomial and all its coefficients are positive, no? Because 265 into 50 is much greater than 81 into 24, yeah, check that out. So 81 into 20s are like 1600, close to 1600, right, it should be 1700 something thereabout, 1700, 1800 something thereabout, and this is much larger than that, I suppose so, right, or is it? Let me check, 265 into 50, 0, 5 5s are 25, yeah, so 2 5 6 are 30, 32, so 3, yeah, it's much larger as expected. It's a brain fade that I had to even calculate this. So this is 13,250, and of course 81 into 24 is nowhere close to that, no. So at least I know that this is positive, this fellow I know to be positive. So I now retain this, of course I can carry on this step and you get the idea essentially, but I am not going to do this nasty calculation. Instead I am going to show you that, of course I cannot avoid this nasty calculation if I do the Routh tabulation, but I somehow still feel that the Routh tabulation is more elegant because you do not have to carry forward this s cubed s and all this, and make these mental adjustments. So let me just take the Routh array, and you will see how all of these coefficients indeed pop up as the Routh array itself. So let me take the s to the 4, s cubed, s squared, s to 1 and s to the 0, okay. All right. So what is the first coefficient of s to the power 4 is 1, coefficient of s squared is 35 and coefficient of the constant term is 24. What about s cubed? The coefficient of s cubed is 9 and that of s is 5, okay. And now we carry out that operation, so we do this multiplication. So what is this? 35 into 9 minus 5. So we have already done this, 315 minus, have I done this? Hang on. Yeah, but I think I am making some mistake, am I? Or did I err somewhere here? 50, did I miss the 50 here? Ah, yes, of course, yeah. So this should be 50, no? Exactly. I misread that. So this is 50. The coefficient of S is 50, not 5. Okay, right. So you see, now what I do here is 9 into 35, which is again 315 as I calculated earlier, minus 50. So it's 265 divided by 9. Yeah. So it's 265 divided by 9. And when I want to evaluate this, then I just extend the same shape, you see. What is here? Since there's nothing here, I always place a 0 here. So what is this? 9 into 24 minus 1 into 0, which is 9 into 24 you get back, and then you divide by 9. So you basically get back 24. Okay. Now you go to the next stage, and you see here this is this ugly calculation that I was showing you here. This is 265 into 50 by 9 minus 9 into 24. Yeah. So 265 into 50 by 9 minus 9 into 24 divided by 265 by 9. So let me just do that rough calculation. 265 by 9 into 50 minus 9 into 24 divided by 265 by 9, which is nothing but, notice the same term, unsurprisingly, minus 81 into 24 by 265. Yeah, so that's the same term, right? So we get back here 50 minus 81 into 24 by 265. And if I want to now go about this term, of course I can see that it's 0 times 0, and this is also a 0. So this is all going to be 0. Of course I didn't do this last bit. Now you can see that what will come back here is this into this. So it's basically this. So this into this minus this into 0, minus 265 into by 9 into 0, that is, divided by this. So this will just give me 24. Okay. So this completes the Routh tabulation, and I see that if I observe the first column, as I remarked earlier, if I observe the first column, or indeed the overall Routh array, as I also remarked in the previous lecture, that if there is some defect in the system, that is, if there is some root on the right half plane, there will be some sign change in some location of the Routh array or the other. Yeah. In other words, if this Routh array has to correspond to a polynomial whose roots are all on the LHP, open LHP, then there cannot be any sign change in any entry of this Routh array, not just the first column. And by extension, of course, then the first column is just a subset of all the entries. So it is also true for the first column as well, right? And the reason being, as I said, now you can see this clearly, at every stage these entries are nothing but coefficients of certain polynomials. If you combine this, you get PS. So it's s to the power 4 plus 9s cubed plus 35s squared plus 50s plus 24. So again, let me remind you that zigzag fashion that we go about. Let me use a different color, right? So we go about it this, reading of the coefficients in this pattern, yeah, and we get P1, PS. Then if you want to get to P1s, you consider these two and you get P1s. How? Again, you read off the coefficients in the same fashion, yeah. So it's 9s cubed plus 265 by 9s squared plus 50s plus 24, yeah. Okay, so I should have named this P3, it's staring me in the face, yeah. Look at P1. So it's basically 9s cubed plus 265 by 9s squared plus 50s plus 24. That is exactly what we are reading off now. 9s cubed plus 265 by 9s squared plus 50s plus 24. Now, if you go to the next two columns, next two rows, I'm sorry, you can read off P2s similarly. It's 265 by 9, yeah, s squared plus this ugly thing, whatever this value is, I'm not going to bother with the evaluation here, yeah, and plus 24, okay. And then if you went one step ahead, here's the claim which I didn't do here. If you went another step ahead and found out P3 of s, you would see it would be nothing but this nasty number times. There's nothing nasty about the number, by the way. It's actually pretty much it can be evaluated. It's a rational number after all, yeah. So it's just this number times s plus 24. And at no stage do you see any sign change. So therefore we conclude, here's how the conclusion works. So you conclude from P3. What can you conclude from P3? P3 is a polynomial of degree less than 2, and therefore if all the coefficients of P3 have the same sign, then P3 is a polynomial all whose roots are on the LHP, and therefore interlacing is valid, right. So this is our stopping criteria. Now because the reverse also holds, so interlacing is valid for P3. So let me reiterate our argument. We have obtained a P3. Up until this point of attaining P3, at no stage have we seen any sign reversal. Yeah, so the final litmus test is this P3. What do we see about P3? The fact that P3 has no sign change in its coefficients. Yeah, if at any earlier stage P1 or P2 had any sign change, the case would be doomed anyway. Yeah, because then that P1 or P2 would not have had all its roots on the open left half plane, because that is a necessary condition to have all signs same, right. So we have already ensured that that does not happen. So now at P3 stage, we are sure that it is an if and only if condition. If there is no sign change in the coefficients of P3, then P3 is definitely a polynomial whose roots are on the LHP. Now because all its roots are on the LHP, it is the same as saying that it satisfies the interlacing property. Now you push this interlacing argument. Because P3 satisfies the interlacing argument, now we go back. Therefore P2 satisfies the interlacing argument, therefore P1 satisfies the interlacing argument, therefore the original P also satisfies the interlacing argument, and we know that satisfying the interlacing argument is the same as having all its roots on the open left half plane, and therefore by looking at P3 up until this stage down the ladder, we can argue along the reverse direction and deduce about the original polynomial. But what about this one sort of a thing that is poking us, this count, this distribution of the roots? We have said nothing about this that justifies why the number of sign changes or the number of sign swaps. Remember, to reiterate, number of sign swaps in first column tells us the number of roots of PS, that is the original polynomial, in the open right half plane, which is the forbidden region where we do not want our roots to be. So this is a claim that is being made, and again, as I said earlier also, I am not going to prove this claim. What I am instead going to try and do here is, I am going to give you a guideline into why this holds, and based on that, yeah, if you read up that paper that I suggested to you maybe in the last lecture or the preceding lecture, yeah, if you read up that paper in transactions on automatic control, it should be understandable. But let me give you a quick hint about why this works. Not actually a hint, kind of a sketch. So look at this. Again, cast your attention back to what happens when you have poles on the left half or roots on the left half plane. For every root on the left half plane, you have one theta changes from delta theta pi is equal to pi by 2. By the same token, exactly the same argument, if you now push for, okay, let me use a different color here. If you use this exact same argument for a root on the right half plane, what happens? So if this is, let us say, pi and this is, let us say, pj. So what can I say about this? It turns out that in exactly the same geometric way, if I sketch this, yeah. So for example, if this is at some omega, this is at some other omega, so you see that the phase is going in a clockwise direction. As I am going from omega is equal to 0 to infinity, this phase for a pole on this right half plane, this goes, yeah, so this is clockwise, which is counted as negative, alright. So therefore, can I not then make this claim for a degree n polynomial with no roots on the imaginary axis, let L is equal to number of roots on OLHP and R is equal to number of roots on open right half plane. Then I can say that N is equal to L plus R. That is the first equation. The second thing I deduce is that now if it was a polynomial with all its roots on the open left half plane, then the total phase change we have seen is n pi by 2. But now what is it going to be? Now consider, so let us say the degree n polynomial is Ps, yeah. Now if you consider the total phase change as omega goes from 0 to infinity, yeah, for this P of j omega, right, that is going to be what? For every root on the left half plane, you will get a pi by 2 net rotation, which is L times pi by 2. For every root on the right half plane, you will get a minus pi by 2 rotation, which gets multiplied by R. So the net phase change is L minus R times pi by 2. So just like this n is called the degree of the polynomial, this L minus R is also given a name, it is called the signature of the polynomial. And notice that instead of giving you directly what is L and what is R, if I give you the degree and the signature, I have actually given you L and R indirectly, because it can be uniquely solved. Okay. So let me call sigma is defined as the signature of Ps, yeah, sigma p. Therefore sigma p is equal to L minus R, and n is equal to degree p is equal to L plus R. So giving you information about signature and degree is the same as giving you information about L and R. You can uniquely solve for these, right. So for example, if I tell you that the degree of a polynomial is 10 and the signature is 4, right. So then you can add those two numbers together, and that is twice L. So L is equal to 7, R is equal to 3. So there are 7 roots on the left half plane, 3 roots on the right half plane. It is uniquely determined. Okay. So this is what one observation is. So now notice, then what is the way to kind of get this distribution? See, we have not given any constructive method, we have just said for the purpose of the proof that we will go on from omega is equal to 0 to omega tending to infinity. But obviously you can understand this is a Herculean task, right. You cannot just evaluate at every point. There are uncountably infinite number of points on this, no. There are an uncountably infinite number of points on this domain. So what are you going to do? So this paper, if you go through, what they have done in that paper is they have strategically chosen some special points here. Okay. So what are those special points? Instead of evaluating at every point, they have chosen some discrete points here. So those points are going to be like this. So suppose you have Pj omega, which is given by P even omega plus j times P odd omega, alright. So suppose you split it up into these two parts, alright. Now look for roots of P odd omega with odd multiplicity. This is important. Okay. So basically every time you have a root for the P odd part, it means that in the range you are going to have the real P and the imaginary P. So every time you find such a root, the odd part is going to be 0. So what is the odd part? Odd part is the imaginary part. So it is basically a real axis crossing in the Pj omega plane. So this is the Pj omega plane, which is your range. This is your domain. To reiterate, this is your domain, this is your range, the Pj omega plane, right. So every time you are looking for such a root, you are basically marking out a point on the real axis crossing. Not just that, if it is a root with odd multiplicity, what does it mean? See, for example, if a function, we know this, right, if you take this x versus fx, so if x has repeated roots at a point, it basically means after touching this point it goes back in the same direction. If it has even times repeated roots, okay, so even multiplicity. On the other hand, if it has odd multiplicity, say there are 3 roots, then you know that going to have some behavior like this. So this is with multiplicity is equal to 3, this is with multiplicity is equal to 2, right. So the way they are strategically choosing these special points are only those points, those roots of the odd part of this polynomial, only those roots of this odd part, maybe I should exclude the j here. So only those roots of this p odd which have odd multiplicity. So what is so special about these fellows? What is special about these fellows is that as soon as you have such a crossing of odd multiplicity, the sign of this odd part changes before and after. So for example, suppose omega I is such that p odd omega I is equal to 0 and omega I is a 0 or root of odd multiplicity. That just means that limit epsilon tends to 0 p odd omega I plus epsilon, the sign of this fellow is going to be the opposite of limit epsilon tending to 0 p odd omega I minus epsilon. Why? It's just a mathematical way of expressing the fact that I have already said. If it's an odd multiplicity, then the sign changes, right. So basically the sign of this imaginary part or this odd part will change after encountering a root of odd multiplicity, okay. So that's what this basically means, alright. Okay. So now, having seen this, what is so special about this particular choice? Now what this paper does is, they say that of course they have some normalization that they do, because normally this polynomial as omega increases it will go to infinity. So the very first stage what they do is, they divide this pj omega by some polynomial of the form 1 plus omega squared to the power n by 2. Notice the special feature of this, that as you keep substituting real values of omega, this is not equal to 0 for all real. There is no real solution to this. So this is just a normalization. On the other hand, it ensures that even as omega tends to infinity, this limit omega tends to infinity is bounded. That is what this serves to do, okay. In fact, this filters out the highest degree coefficient, you will see. Why? Because you just divide by omega to the power n above and below, and you will see that that is the highest degree coefficient, okay. So that is what this normalization does. So what then they do is, the interlacing property of this is just like some constant scaling only, you can treat it like, right. So if this is interlacing, then this overall function, they call it pf j omega is equal to the original polynomial that you had divided by this 1 plus omega squared to the power n by 2, okay. So everything that you deduce about the roots of pj omega are true of the roots of pj omega, pfj omega, this is just, the scaling helps to ensure that this does not go unbounded as omega tends to infinity, okay. So next what we note is that now, notice, and this is the interesting bit. So I am going to draw this here. So this is the real part of P and this is the imaginary part of P. Now suppose you have a violation of the interlacing property, so that means that after encountering a 0 of the imaginary part, you encounter the next 0 of the imaginary part here, or maybe here, without first encountering a 0 of the real part somewhere on the imaginary p axis, okay. So these two violate interlacing, So if you want to now study, remember you have split this up into zeros of the odd part, zeros of odd multiplicity of the odd part, okay. So call this omega 1, call this omega 2, omega 3, like this, so on and so forth. Now what this paper focuses on is the change in angle between omega I and omega I plus 1 of this pf j omega, Why is that interesting? That is interesting for the following reason. Notice, if, and what are omega I? Omega I and omega I plus 1 are two consecutive. What do you mean by consecutive? Consecutive means as you go up this imaginary axis, there is this ordering, okay, one is greater than the other. So, there is a nice ordering of these numbers, okay. So, when I say consecutive, if you go up, then you encounter omega I, and then between omega I and omega I plus 1 you do not encounter any other root of odd multiplicity for the imaginary part, okay. So, these are two consecutive zeros or roots of odd multiplicity of the imaginary part, that is Pf imaginary j omega, yeah, is equal to 0, okay, right. So, now I can of course get rid of this j here, because it is just a function of this, yeah, it is just a function of omega, right. So, now notice what happens. The claim is that this is nothing but equal to, yeah, this is nothing but going to be equal to the Pf real at omega I, the sign of that. So, the signum function is basically plus 1 for positive argument, minus 1 for negative argument, and 0 for 0, yeah, that is how the signum function is defined. Alright. So, now what they are doing is, you notice that if you take this Pf real, remember these are roots of the odd part, okay, multiplied by Pf odd at omega I plus epsilon, where epsilon tends to 0. Notice how this holds. Yeah, I will just give you an illustration of why this is true. Notice these two cases which violate interlacing, what happens? Yeah, look at this. If this is your omega I and this is omega I plus 1, or let us say this is omega I plus 1, whichever way it is, I do not care really. If you have encountered two roots of the odd part without encountering a root of the imaginary part in between, of the real part in between, I am sorry, then this is how the picture would look. This is how your plot of Pj omega would look, yeah. It is not interlacing. For interlacing it would have had to go like this, no, it is not doing that. So, in this case what happens? Look at the, okay, I missed the signum here, and this is also a signum. So, I am missing these signums here, okay. This is a signum, this is a signum. So, signum of this minus the signum of this whole multiplied by the signum of this, okay. So, why is this true? Notice that now if you look at the value of the real part at omega I, this is positive. So, this is plus 1. What about this? This is also positive, because both are on the real positive real axis. So, this is also plus 1. So, this then turns out to be 0, and indeed if you now look for the total phase change as you went from omega 1 to omega, what is the phase at this? So, basically up until this point the phase kept increasing and then the phase kept decreasing. So, in going from omega I to omega I plus 1, that is from let us say omega 1 to omega 2 here, as you went from omega 1 to omega 2 here, this total phase change is net equal to 0. On the other hand, if you had the interlacing satisfied, so let us say this is your omega P at P odd, or rather what have I, actually these are not omega I, am sorry, this is kind of a misnomer. So, this is basically the P real at omega I plus 1, and this is P real at omega I, and this is also similarly P real, because this is a Pj omega plane, remember. So these are basically the real parts of the polynomial, not the real part of omega, okay, right. So now notice if this corresponds to my p real omega I and this corresponds to my p real omega I plus 1, right, then what happens? Go back to this expression. Here you see that there is a net change of pi. So this expression should also give me pi. How so? So look at this. This is now plus 1, this is now minus 1. So 1 minus minus 1, that's 2. Okay, I have also missed a pi by 2 here. So this is all ad hoc adjustment that I am doing here. Sorry about that. So this is the net phase change, so there should be a pi by 2 here. Okay. So now it's a little clumsy, I apologize for that. But now you see what happens here is that here this is positive, this is negative. So if you plug it in this expression, this is positive now and this is now negative 1. So plus 1 minus minus 1, that's 2. So 2 times pi by 2 is pi. And what about this? Look at this. This is nothing but the value of the odd part if you go just epsilon ahead of omega I. So what if you go epsilon ahead of omega I, that is some point here. What is the value of the imaginary part? It is positive. So therefore you see that this turns out to be indeed equal to pi, which it should from this sketch. The net phase change as you go from this, as you go from omega I to omega I plus 1, the net phase change of p is pi, and this satisfies this. So I urge you as a part of an exercise to check out the different special cases, other cases. So for example, suppose you have your omega I here and your omega, I mean pj of p real of omega I here and p real of omega I plus 1 here. Yeah, in that case also you will see that the net rotation as expected should be pi. On the other hand, if these roles are reversed, you would see that this expression actually spits out the right result. So now what they are saying, what this paper does is, instead of summing from entire 0 to infinity, what this paper does is, they say now, let me take summation delta, delta omega I to omega I plus 1 of this p f j omega, p f j omega, okay. So this is the sum that they are interested in, where I goes from 1 to as many roots there are with odd multiplicity of the even part, okay. And then finally you say that omega m plus 1 you assign it to infinity, okay. So that is how you go about it, okay. And this will actually tell you the net phase change. This is nothing but the net phase change from 0 to infinity of pf j omega. And it turns out, if you go follow through with this paper, you will see that eventually this turns out to be nothing but equal to the sigma of pf, yeah, times pi by 2. That is the crucial bit, okay. So now by counting this, it turns out that this gives you nothing but the signature. That is the difference between the number of roots on the open left half plane and the number of roots on the open right half plane, okay. So this gives you the signature, you already know the degree, yeah. So if you can sum this up carefully, you will have your answer. But then the question still remains, how do you sum this up? It turns out, and that detail is there, it's a nasty looking expression. I will not go through that because it's really not that important. But the point is that there is a very nice way of doing this, because this has a closed form expression given in that paper. And I urge you to go through the paper, and I also insist that it is not very difficult to understand how this closed form expression is arrived at. It is just a bit of bookkeeping. So the interested students among you should visit that paper and read through it, and you will find that, in order to find this, we have reduced it to the task of finding these individual terms, and these individual terms have a closed form expression. So you can sum them together, and eventually it so happens that it turns out, that this is nothing but the sign of the leading coefficients, okay. So this, you see this signature, yeah, has this close relation with an and an minus 1 are closely related to this sigma. How? Again, I'm going to give you the final expression sort of. So let's say, suppose you reduce n degree p to n minus 1 degree q, okay, then the signature of q minus the signature of p, it turns out by this clever bookkeeping, okay, and that is why it is very interesting. It will just take you a bit of time. Now that I have explained this, it should not be too difficult to follow. This is equal to, yeah, the sines of an times an minus 1. And what are these an and an minus 1? If you now cast your attention back to the Routh array that we just drawn towards the beginning of this class, you see the an and the an minus 1 are nothing but the highest degree coefficients of two successive polynomials, like, so p has the highest degree s to the power 4 coefficient 1, p1 has the highest degree s cubed coefficient 9, p2 has the highest degree s squared coefficient 265 by 9. So if you take the product of these two, okay, all that it says is that if you take the product of these two, yeah, and if this is plus 1, okay, so if this is, if they are of the same sign, so if an and an minus 1 have same sign, then sigma q minus sigma p is equal to plus 1. What does that mean? Look, this has a, q has a degree n minus 1, p has a degree n, okay. So in going from p to q, you have lost 1 in the degree, okay. So this is equal to nothing but L1 plus R1, where L1 is the number of open left half plane roots of q in L and R1 is the number of open right half plane roots of q in, right, in this polynomial. And similarly this has n is equal to L plus R. So obviously we know that the net sum of L plus R has reduced by 1. Now if you know that the net difference is also reduced by 1, what can you conclude? The only way that this can happen is, yeah, the only way that this can happen is, okay, maybe I should reverse the order, probably L sigma of p minus sigma of q. Let me think about it a bit. Yeah, so let's do a reverse calculation, maybe. So I am not referring to the paper, so I have forgotten that expression, but yeah, we should be able to figure it out. So suppose you have L plus R is equal to n and L1 plus R1 is equal to n minus 1, right, and let L1 is equal to L minus 1, okay. So therefore L1 minus R1 is equal to L minus 1 minus R1, but R1 is then equal to R. So this is basically sigma p minus 1 is equal to sigma q. So sigma q minus sigma p, yeah, so it should be minus 1, sorry about that, I think it should be a minus 1, please check if I am making a mistake. So the point is, from going from p to q, you have lost one root, yeah, because the degree has reduced by 1. Now what sort of a root have you lost? Have you lost a root on the open left half plane, or have you lost a root on the open right half plane? So if the sign does not change, yeah, if the sign does not change, it turns out that you have actually lost a root on the open left half plane, okay, yeah, so I am correct about that. So this is basically the reduced degree polynomial, this is the original polynomial, okay. So this is the key, this is what allows you to count the distribution, okay. So if you have reduced the degree of the polynomial from, let us say 20 to 19, okay, and the original polynomial had 10 on the left half plane and 10 on the right half plane. Now if you have gone down to 19, and now you have 9 on the left half plane and 10 on the right half plane. So then you have not lost any root, at least the number of roots you have not lost on the right half plane. You have only suffered a decrease in the number of roots on the left half plane. Okay, so that is what this signature decrease implies. Okay, so therefore this is when we say that there is no sign change, and therefore, yeah, we are actually well on our way to proper bookkeeping. Okay, so this is why this counting and this distribution works. So that is why the Routh does not tell you only whether all your roots are on the left half plane, but in case they are not, it also keeps track of how many are there on the left half plane and how many are there on the right half plane. We will take some more examples and we will consider some singular cases in the next lecture, which should also be interesting. Thank you.